Yeah. Okay. Okay. All right. So I will just go over an example of calculating a balanced outcome. Very simple. All right. So that's all I have planned for today. So a quick reminder what we were doing. So we were doing the network bargaining game. And what we are having is we have a graph. And there are some values on each edge, right? So you have a graph, and you have some value on each edge, right? So this is a terrible graph. So let me try to write that again. Okay, so 3, 4, 5, 9, 7, 6, 4, 2, something like that. All right, so and the idea is you want to do a matching. So for example, you might have a matching between these two, between these pairs. And what you want to do is split the values between them. So only those that are matched will split the values. So players on either end will split 3, and players on either end will split 2. Okay. And for a stable outcome, what we need is look at the outside options and make sure that what you receive is greater than or equal to any outside option of that player. So if you have, say, a very simple example like this, where I have, say, 10, 5, 2. Let's say I split the 10 in this way, 7, 3. Okay, so if I split the 10 into 7, 3, the outside option for player 1, for this player, outside option is 5. 7 is greater than or equal to 5, so that's good. The outside option is 2, and 3 is greater than or equal to 2, so that's also good. So that's a stable outcome. Okay. Okay. But to be balanced, things are a little bit more delicate. Okay, so in that balanced outcome, I need something like for each UV. And if you look at the difference between the value you get minus the outside option, it has to be the same for either end of the matching. Okay, so the equation here is xu minus alpha u, the outside option for u, is equal to xv minus alpha v, the outside option for v. Okay, so yeah, so that is what happens in a balanced outcome. Okay, I don't know if I can calculate this off the top of my head, but I guess we're off by 1 and off by 2, so maybe 6, 4 will do. No, that's not right. 7.5 and 3.5. That's not right either. So there's a little bit of trying there. No, 7.5 and 2.5. 6.5 and 3.5. Yeah, 6.5 and 2.5 will work, right? So in this case, the outside option here is still 5. So 6.5 minus 5 is 1.5. 3.5 minus 2 is also 1.5. So this is balanced. Okay. All right. So there is a little bit of a try and error involved when doing a balanced outcome. Stable outcomes are a little bit easier to do, but balanced outcomes are slightly harder. All right. All right. Okay. So how do you find a balanced outcome in a more systematic way? Okay, so we're looking for a way to get a balanced outcome in a more systematic way. So so the first step is so to find the balanced outcome. We first need to find a maximum weight matching, right? So we have stated in class without proof that you need to have a maximum weight matching in order to have in order to achieve balanced outcome. And even if you have a maximum weight matching, it might not guarantee a balanced outcome exists. And so we need to start. We start with a matching of maximum weight. Okay, so that's a maximum weight matching problem. We will not go through how to do this. That's an optimization problem, and that is a little bit deeper for harder examples. For our examples, we will mostly just do by inspection. This is a maximum weight matching. Okay, all right. Okay, so you want to start with the matching of maximum weight. Okay, and then you will then try to figure out what could be the payoffs for the players on the ends of the matching edges. Okay, and what we will do is we will use a linear program to do that. To find a payoff vector, P of x, that gives a balanced outcome. Okay, so we'll try to use a linear program to find a payoff x that gives a balanced outcome. Okay. All right. So what I will do is just do an example, and then we'll show you the linear program, and then maybe we'll get the solver online to solve it, and maybe that will work. Hopefully it works. Okay, so I will be very adventurous and give you a random example. I think I have this graph in mind, but I have not decided on what would be the the weights on the edges. So I'll start putting random weights. So maybe that's 3, 5, 6, 7, 4, 9, 2, something like that. That looks like those are weights. Okay, so that's good. All right. So there are a few matchings, and we want to find the maximum matching in this diagram. So so if you just do 3 and 4, that's 7, 10 for 3 and 7, that's 8, that's 10, that's by itself is 9, and we have 12. Okay, so that is our maximum matching. Okay, so there you go. That's our maximum matching. Maximum weight matching. Okay. All right. Okay. Now, the first thing we are going to do is to say that those vertices that are not matched, those two here, they will get 0 automatically, right? So they get 0. They get nothing because they're not matched, so there is no payoff for them, right? So vertices not matched receive 0. Yeah. Okay. All right. Okay, so now we just have to figure out what are the values for the vertices that are matched. Okay, so what are their values? So we have 4 vertices that are matched. So these two and these two. Okay. So let's give them a name. So let's say these are A, B, C, and D. Okay, so those are the 4 vertices that we want to figure out. So we want to figure out XA, XB, XC, XD. Okay. All right. Okay. And there are 2 types of equations that we will try to get. Okay. So the first equation is that their sum must be equal to the weight of the matching edge itself, right? So A plus B here has to equal to 5, and C plus D here has to equal to 7. Okay, so weights on matching edges. I guess no payoffs on either end of matching edges. Sum to the weight. Sum to their weights. Okay. Right. So in this case, we have A plus B is equal to 5, and we have C plus D is equal to 7. Okay, I'm really worried about the 9 in the middle. That might cause some trouble, so maybe I'll change later. If we come up with no solutions, then that 9 and that 6 is probably a problem, but we'll change things around if we need to. All right. Okay. So that's the sum of the matching edges. So the either end of the matching edge, they must sum to the weight of the matching edge. Okay. And the other is the balance equation, right? So we have the balance equation. Right? So in this case, if you look at A, the payoff, so if you look at this edge here, A minus the outside option for A is equal to B minus the outside option for B. And the same thing for the other one, C minus the outside option of C is equal to D minus the outside option for D. Okay. Right. And this is where things get a little bit tricky, right? So because these outside options, they do depend on the values of A, B, C, and D. Okay, so if you look at A, for example, you can get outside options from here, here, or here. And so there are 3 places where you might get outside options. Okay, this one is always going to be 3, right? So there's no question about that. Okay, but this one is going to be 6 minus C, right? So whatever value C is 6 minus C there. And the outside option here is 9 minus D. Okay. Okay. And also the outside option has to be non-negative, right? So I should mention that outside options are non-negative as well. Okay. Okay. So if we look at, say, the outside option for A, here, outside option for A, there are 3 choices. It is the max of 3. Okay, so the 3 coming from here. 6 minus C. Okay, so that is the outside option coming from here. And also 9 minus D. Okay. It's my 9 minus D. All right. And then we can do the same thing for the other ones. Outside options for B. Outside option for B, there's only one choice here. But to make sure that we don't run into problems, we want to make sure that this is a max of 0 and the 4 minus D. Okay. Eventually, it won't matter because we're going to have a linear program, so everything is non-negative to begin with. But we're just writing it down formally here for now. And outside option for C, there's only one choice as well. So it's either 0 or 6 minus A. Yeah. Right. And then the outside option for D is going to be 3 choices. It's either 2, which guarantees that there is no, it's at least 0 for sure. And 4 minus B and 9 minus A. Okay, so those are the outside options. Okay. Okay, so far so good. Those are just from the definitions. Okay. Okay. All right. But here's the question. Here's the problem. This is not a linear function, right? So if we treat these outside options as variables, the max thing is not a linear function, right? So it's dependent on C and D. It jumps around. Okay. Okay. So that's why we need to go back to a long time ago when you did linear optimization or just the optimization course. We could turn this into several inequalities, and then we will do a minimization to ensure that alpha A does take on the value of the maximum of these three. Okay, so here is a trick from CO250. Okay, on converting maximization. Converting, let's say, some y is equal to max of, say, I, j, and k. Okay. Okay. So what you would do is you want to say y is the max of these, so y has to be at least each of these. Y is at least I, y is at least j, and y is at least k. Okay. Okay. All right. But you don't want y to be infinitely large, so you're going to say something like min y to do that. Okay. All right. So if you look at I, j, and k, those are the values do you want to take the maximum of, and y certainly has to be at least each of these. And when you minimize y, then it's going to take on the exact value of the largest of these three. Okay, so that is the trick we get from linear programming. Okay. 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 So what we can do here is for our outside options. Okay, so for our outside options, if we look at this equation here, alpha A is greater than equal to max of those three. We could do alpha of A. Let's start with minimizing all four of them. Okay, so minimizing the sum of each of these will be the equivalent of minimizing the individual variables. And we have alpha of A is at least 3. Alpha A is at least 6 minus C. And alpha of A is at least A minus D. Okay, so this together with this corresponds to that. Okay, so alpha A is the max of these three. When you convert it into a linear program constraints, it becomes these three inequalities and minimizing the alpha of A. All right. All right, and we can do the same thing for the other three. So alpha B is at least 0, and alpha B is at least 4 minus D. This one is going to get ignored because we will always have a non-negativity for our variables, and alpha C is at least 0. Alpha C is at least 4 minus A. And we won't care that much about that. And alpha D is at least 2. Alpha D is at least 4 minus B. And alpha D is at least 9 minus A. Okay. All right. Okay. So these are all the elements I need for my linear program. Okay, so I have a minimization, minimizing the sum of these four outside options as variables. Get these constraints here for our outside options. And we also have these four equations here. Okay, so the matching edges will sum to their weight and the balance equation holds for the matching edges. Right? So combining all of them, we should be able to solve for a balanced outcome here. All right. All right. So the rest of it is just crunching numbers. So let me try to combine them into an LP. So the LP, so it's going to be minimizing 1, 2, 3. So minimizing alpha A plus alpha B, alpha C plus alpha D. Okay, and I will make this our A, B, C, D. And I will only write down the coefficients for this. Right, so A plus B is equal to 5. So that means that A plus B is equal to 5. C plus D is equal to 7. Okay. So C plus D is equal to 7. I guess I should just do this as 1, 1, 1, 1. And minimize those things subject to these constraints in kind of the coefficient form. Right? A minus alpha A equals to B minus alpha B. So A minus alpha A minus B plus alpha B is equal to 0. So A minus alpha A plus B, no, minus B plus alpha B is equal to 0. Okay, and similar for C and D. C minus alpha C minus D plus alpha D is equal to 0. I'm hoping that I didn't make any mistakes. C minus alpha C minus D plus alpha D is equal to 0. Okay, that's good. All right. All right, so then the rest of that, right, so alpha A is at least 3. Alpha A plus C is at least 6. Is that a 9? That's a 9. Okay, here's a 9. Okay, so alpha A plus D is at least 9. Okay, alpha B plus D is at least 4. Alpha C plus A is at least 4. And just 3 more. Alpha D is at least 2. And alpha D plus B is at least 4. And alpha D plus A is at least 9. And everything, all variables, are at least 0. Okay. All right. So that is the linear program that we are working with. And we just had to solve it. We don't we certainly don't want to solve this by hand. Okay, so there are lots of ways you can solve this with online tools. So what I'm going to do, so should alpha C greater than or equal to 6 minus 8, that is possible. So let's see. Alpha C, alpha 6 is greater than or equal to 6 minus 8. Yes, that is correct. Thank you. All right, so let me change that. 6 minus A, and alpha C is greater than or equal to 6 minus A. So that's also 6. Excellent. All right, thank you. All right. Hopefully that's all the errors I have. Okay, so what I'm going to do is I'll switch the screen to one of the online solvers I have used before, and that always seems to be okay. It will have Google Ads, but I'll try to remove the Google Ads in there. Okay, so I'll share a new screen here and as my Google. So I have 8 variables here, and how many constraints I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 12 constraints. Okay. All right. Oh, that's free shipping. Great. So we will minimize the four alphas. Okay, so a plus b is equal to 5. C and D. You don't have to use this tool. You can use any tool you want. And here's the balance equation. 1 minus 1 minus 1, 1 is equal to 0. 1 minus 1 minus 1, 1 equals 0. And then we have the minimize things. Okay, so C alpha A is at least 6. C alpha A, and then D alpha A is at least 9. I hope there is a solution. D alpha B is at least 4. And then A and alpha C is at least 6. Just alpha D is at least 2. And then B alpha D is at least 4. And A alpha D is at least 9. Okay. So that is hopefully the linear program that we had to do. I really hope this works. Did I miss something? No, I didn't miss something. Okay. That looks fine. Just double check. All right, so I'll just run this. I'll continue, and then I'll have a direct solution. There is a solution. Nice. Okay, so the solution is 5025. Does that work? Okay, well, so let's go back. So 5025 is supposed to be the solution. Let me write it down. All right, so let me get back to the screen here. All right, so let's copy this diagram here. And our solution is 5025. Let's see if it actually works. All right, so 5, 0, 2, 5. Okay, all right, so let's check if this works. All right, so I really hope it works. So the outside option here is 1. So, well, actually, technically it's 0. Well, I guess it's 0. No, it is 1. Okay. All right. So that... All right. The outside option here is max of 3, 4, or 4. So the outside option here is 4. That doesn't check out. Okay. The outside option here is just 1. The outside option here is there's 4 here, 4 here, and 2 here. So that is going to be 4 here. This one does check out. Okay, so 2 minus 1 here is equal to 5 minus 4. Okay.
Isn't
Oh,
the outside option for B 0? Like it still doesn't work, but
it still doesn't work. Yeah, but it should be 0. Yeah. So that should be 0. Is there something weird going on here? I don't know. Okay, so maybe I did something wrong with the equations and inequalities. Just double check. 3, 6, 9, 4, 6, 2, 4, 9, 5, 7. Uh, so it should work in general. All right. Also, it's the outside option of B that is the problem, and outside option of B is at least 0 and also at least 4 minus D. It does say the outside option is 0. So 5014 are the outside. Oh, 5014. Huh. So the linear the optimal solution is telling me that the outside option here is 5, but that doesn't look right. Okay. Anyway, so if I can find the fix after the tutorial ends, I will fix that here. But for now, this should work in general. This should work in general. All right. So this is a way of finding balanced outcomes using linear programs. All right, good. A few things could have gone wrong somewhere in there, but I can find what is wrong with it right now. Actually, maybe I can find something wrong with it right now. Alpha A is at least 3. Alpha A is at least 6 minus C. And alpha A is at least 9 minus D. Three, 6, 9. Alpha. Yeah. Okay. Anyway, I think that's all I'm going to do. Any questions you have? All right. Okay. All right. So I'll stop recording.